Hello friends, welcome to my YouTube channel. In this session, we'll try to see about the Maxwell's equation. So I have given a summary of the Maxwell's equation in the table form. So Maxwell's equation in the final form, otherwise in the integral form, we will see. So you know that first Maxwell's equation is given by the Gauss law, and the second Maxwell's equation was derived from Gauss law for magnetism, and the third law was derived from Faraday's law of induction, and the fourth law is from Maxwell's circuital law. So Maxwell's first law, otherwise which was derived from the Gauss law, is in differential form is expressed as del dot D is equal to rho V. The same in integral form it is given as closed integral of S d dot ds is equal to integral rho V into dV. So the remarks is we have derived this Maxwell's first equation from the Gauss law. The second law is del dot B in the differential form it is del dot B is equal to 0, and in the integral form it is surface integral B dot ds is equal to 0. So it was derived from the non-existence of isolated magnetic charge. The third law, which was also called as the Faraday's law, in differential form is expressed as del cross E is equal to minus of dou B by dou T, and in the integral form it is expressed as integral L E dot dl is equal to minus of dou by dou T integral S B dot ds, that is converting the line integral to surface integral. The fourth law was expressed from or derived from Ampere's circuital law. In differential form, it is expressed as del cross H is equal to J plus dou D by dou T, and in the integral form, it is expressed as integral L closed integral L H dot dl is equal to integral S J plus dou D by dou T dot ds. Now we'll see how we have derived all these Maxwell's four equations in detail. So first we'll consider the Maxwell's first equation. So what was the Faraday's law? So the Faraday's law for the induced EMF is expressed as VMF is equal to minus of d lambda by dt into V, right? And again, what is Lenz's law? Already we have seen in the previous session. Lenz's law is nothing but the induced EMF V is equal to minus of n into d phi by dt, where n is the number of turns and phi is the flux density. So therefore, the induced EMF is given as closed integral L E dot dl, where your phi is given as integral S B dot ds. So substituting your phi in your induced EMF, we can write it as induced EMF is equal to integral S B dot dou B by dou T into ds, right? Now we'll see Maxwell's equation, the continuation of it. So your integral L E dot dl is equal to integral S dou B by dou T into ds. So Stokes theorem is nothing but converting your line integral to surface integral. So the formula is line integral of H dot dl is equal to integral S del cross H ds. So using the Stokes theorem, we'll try to convert this equation. So this third equation can be rewritten as integral L E dot dt, and as like the Stokes theorem we'll try to write it. So it is E dot dl line integral is equal to, can be written as surface integral of del cross E into ds, replicating this Stokes theorem. Now you go for the third equation again. So in the third equation, instead of line integral E dot dl, we'll just substitute the surface integral. So that surface integral del cross E into ds is equal to minus of surface integral of dou B by dou T into ds. Therefore, the left hand side and the right hand side both are surface integral. So we can eliminate those integral parts and we can write it as eliminate the integral as well as the ds term, since both are present in the left hand side and the right hand side, and we can write it as del cross E is equal to minus of dou B by dou T. So this is our Maxwell's first equation. The next one is Maxwell's. We'll go for the Maxwell's fourth equation. So fourth equation was derived using the Ampere's circuit law. So integral L H dot dl is equal to I. This is the Ampere's circuit law, the definition of Ampere's circuit law. So this can also be written in terms of surface integral, that is double integral J dot ds, where J is the charge density. surface charge density. So the total current involves both the conduction current and the displacement current. So your current can also be written in terms of line integral, which is the Ampere circuit law, that is integral H dot dl. It can also be written in terms of current conduction, current density, that is double integral J dot ds. Now this current I can also be, this current I is contributed because of conduction current as well as the displacement current. Now we'll see what is conduction current. A current through a resistive element is called as conduction current. I'll repeat, a current through a resistive element is called as conduction current. A displacement current is a current through a capacitive element is called as displacement current. Now according to Ohm's law, the current through a conductor of resistance R is given by I is equal to V by R. This is the basic Ohm's law formula. So according to Ohm's law formula, the current through a conductor of resistance R is given by IC is equal to V by R. So where R is nothing but rho L by A, where rho is the resistivity, L is the length of the conductor and A is the area of the conductor. So sigma can be written as 1 by rho, where sigma is called as the conductivity. Therefore, in the place of 1 by rho, I'll try to replace sigma in the equation R. So R can be written as L divided by sigma A. Therefore, IC is equal to V by R. So, in the place of R, I'll try to replace this equation. Therefore, IC can be conduction. IC is not the collector current over here. It is called as the conduction current. So, the conduction current is equal to V by R. So, V divided by, this is my R term, that is rho L by A, right? Now, your conduction current is equal to V into sigma A divided by L, because 1 by rho is nothing but sigma. So sigma A divided by L. So therefore we can also write V is equal to E into L. There is another formula, V is equal to E into L. Therefore the conduction current can be written as E L sigma A divided by L. So this can be simplified as E sigma A, right? Where L and L will get cancelled, therefore we can write it as E sigma A. So the conduction current density Jc can also be written as conduction current divided by the area of the conductor. And therefore we can write it as Ic by A is equal to E sigma, or else we can write the conduction current density Jc is equal to sigma into E, right? Now, so as I said you, this current is contributed because of conduction current and because of displacement current. Now we found an equation for conduction current density and the conduction current. Now we will see what is displacement current. So displacement current is nothing but the current which is passed through the capacitor element. So current through a capacitor is called as displacement current. So the displacement current is represented by the terminology ID. So it is nothing but dq by dt, where q is the charge of the element. It can also be written as V into C. So therefore ID is equal to, because it is the current through a capacitor, that is called as displacement current. So the charge Q is expressed as V into C. Therefore ID is equal to C into dV by dt. Substituting the value of Q over in this equation, so you get C into dV by dt, where C is nothing but the capacitive element, which is equal to epsilon A by D, where epsilon is the permittivity of the medium, A is the area of the plate of the capacitor, and D is the distance between the two plates. Now ID is equal to epsilon A divided by D into dV by dt. Because we know the C term over here, ID is equal to C into dV by dt. In this equation, we will try to replace the C by this term. Therefore, you get ID is equal to epsilon A by D into dV by dt. So, V can also be written as E into D. So, when you replace this V with the E into D and you differentiate it with respect to T, you will be cancelling out the D term and you will be getting the displacement current is equal to epsilon A into dE by dt, right? Now this A in the right hand side, I'll try to bring it to the left hand side. Therefore, ID by A is equal to epsilon into dE by dt. We know that D is equal to, D is the displacement current density, sorry, JD is the displacement current density, where D is equal to epsilon into E, that is electric field intensity and the electric flux density. So E is the electric field intensity and D is the electric flux density. So the relationship between electric field intensity and electric flux density is D is equal to epsilon into E. So here JD is equal to sigma into E. We know that JD is equal to sigma into E. So this ID by A is nothing but JD, and this epsilon into dE by dt can be written in terms of D. So it is dou D by dou T. Now, what is our Ampere circuit law? Integral H, integral L, H dot dl is equal to I, the current I. So, the current I can also be expressed in terms of two currents, that is conduction current and displacement current. So, we found the conduction current as the JC, that is displacement current density, and similarly plus JD. This is conduction current density plus displacement current density into ds. So earlier in the previous slide we have seen integral L H dot dl is equal to I, which can also be expressed in terms of surface integral J dot ds. Instead of that J, I have replaced with conduction current density and displacement current density. Therefore, it is double integral Jc plus Jd into ds. Now, what is this Jc we have found in the earlier slide? It is sigma e. What is this Jd we have found? It is dou d by dou t into ds. Right? So, your I is equal to, otherwise H dot dl is equal to double integral of s j plus dou d by dou t into ds. Now we will try to apply the Stokes theorem, because this side, the left hand side is in line integral, the right hand side is in surface integral. We cannot solve it, so we need to make both the things into the same surface integral. So we'll try to implement the Stokes theorem. So Stokes theorem is nothing but H dot dl is equal to surface integral of del cross H into ds. Now we'll try to implement the Stokes theorem to the left hand side, converting the line integral to surface integral. Then this equation 1 becomes surface integral of del cross H into ds is equal to surface integral of j plus dou d by dou t into ds. Now the left hand side and the right hand side both are in surface integral. Therefore, we can remove this integral and the ds term, and therefore we can get del cross H is equal to j plus dou d by dou t. Or else we can also substitute the terms of j and d, and therefore we can expand the equation as del cross H is equal to sigma e plus epsilon into dou e by dou t. So this is your Maxwell's fourth equation. Now coming to the Maxwell's third equation. So Maxwell's third equation is derived from the Gauss law. So what is the Gauss law? Integral d dot ds is equal to the charge q. Okay, so we can also write this in terms of volume integral. So integral rho into dv is equal to q. So similarly, we can, since both the d dot ds is also equal to q and rho dot dv is also equal to q, we can equate these two things because both are equal to q. We can equate these two equations. So surface integral of d dot ds is equal to volume integral of rho dot dv. Now you try to apply the divergence theorem. Why we need to apply the divergence theorem? Because left hand side is in surface integral, right hand side is in volume integral. Now applying the divergence theorem, you can convert the surface integral to volume integral. So let us take the left hand side, which is of surface integral t dot ds. Now how will you convert it into volume integral? By using the divergence theorem. So the theorem is nothing but volume integral of del dot d into dv. Now substitute this 2 in the left hand side of 1. So you will be getting both the sides as volume integral. Therefore, volume integral of rho dot dv is equal to volume integral of del dot d into dv. Now both the sides are volume integral, both the sides are dv, so we can eliminate those terms, and therefore you can get rho is equal to del dot d. So this is your Maxwell's third equation. Now coming back to the Maxwell's second equation, surface integral of B dot ds is equal to 0, which was derived from magnetic laws where the total flux in any closed surface is equal to 0. Okay. Now applying the divergence theorem, we can convert the surface integral to volume integral. So earlier also we have seen what is divergence theorem. So surface integral of B dot ds is equal to converting into volume integral of del dot dv equal to 0. Therefore both the sides, so we can conclude that del dot b is equal to 0. So this is your Maxwell's second equation. Now again summarizing the Maxwell's equation in the phasor form. So in the differential form and in the integral form. So in the differential form, Maxwell's first equation is del cross H is equal to sigma plus j omega epsilon into E, whereas in the integral form it is line integral of H dot dl is equal to surface integral of sigma E plus j omega epsilon E into ds. Right? Now, in differential form, Maxwell's second equation is written as del cross E is equal to minus of j omega mu into H, whereas in integral form, it is line integral of E dot dl is equal to minus of mu into surface integral of j omega H into ds. Similarly, in differential form, Maxwell's third equation can be written as del dot D is equal to rho v. In integral form, it is written as surface integral of d dot ds is equal to volume integral of rho v into dv. And the Maxwell's fourth equation in differential form is given as del dot b is equal to 0, and in the integral form it is written as surface integral of b dot ds is equal to 0. So hope you all understood how we have derived all the four Maxwell's equation from the Gauss law, Ampere circuit law, and from the magnetic laws. Thank you all.